This is the second module on the logistic equation, and the goal here is to figure out how we solve the logistic equation. If you remember, the logistic is this expression here in the box. Finish drawing my box. And it says that the rate of change of the total number of individuals n in a population with respect to time t is given by the product of two terms. The first term is a term that's directly proportional to the population size, so it's called a linear term. The second thing that we multiplied by is a term that decreases as n increases, so the product of the two is nonlinear. And as we pointed out in the first module, this equation has an equilibrium at this value k. That's the value of population at which population size will not change anymore. The other equilibrium is n equal to 0. The goal here is, suppose that at some initial time, t equal to 0, we'll call it, we know that the population size is n0. What is the population size at some later time, say t1, greater than 0? That means we've got to integrate this sucker. And so the first step is to take our equation and write it this way, where we've collected all the n terms on the left and all the t terms on the right. Which raises the question, why is little r on the right-hand side? Why don't we keep it on the left-hand side? The reason for that has to do with dimensionality, and it's an important thing that ecologists tend to forget, but which you should not. If you recall what r is, it's a growth rate, which means its dimensions are 1 over time. And so the right-hand side of this equation has a term r, which is 1 over time, multiplied by a dt, which has dimensions of time, and so it's a dimensionless product. And the left-hand side, which involves just numbers, is also dimensionless. So the dimensions here are, in fact, the same on both sides, which is why we want to keep r on the right-hand side. Now, to solve this thing, we need to integrate both sides. And we're going to call the sides the LHS, or left-hand side. It's here. And the RHS, or right-hand side, which is here. The RHS is pretty simple, right? And so we ought to be able to integrate that. The LHS, on the other hand, looks messier, and so we're going to have to figure out how to deal with that. So the next step here is to do the integration of the two sides, but before we do that, we need to specify the limits of integration. So we start at t equal to 0 with n equal to some n0, and we end at some time t1 with some n1, and we don't know what n1 is. That's what we want to find out. As I said, the RHS is easy to integrate. Integral of dt is just t. And so the right-hand side, the RHS, is just r times the elapsed time, t1. And we're going to number this equation. That's why I've written down here equation number, and the equation number in this case is 1. We're going to keep doing this for important equations as we go. The LHS, on the other hand, as I've said, is not so easy. The left-hand side is this thing in the box here. And that looks like it might be a difficult thing to integrate. But if we look at the denominator, we see that it's the product of two things, which means it ought to be possible to write this as the sum of two simpler fractions. And you can see that the denominator is going to work out. In order for the numerator to work out, we say the first fraction is multiplied by some unknown capital A, the second fraction by some unknown capital B, and the issue is, can we find an A and a B that make this equal? And inspection of this thing, or some easy algebra, shows that you can do this if A equals 1 and B equals 1 over capital K. This general method of expressing things where you've got 1 over some complicated looking fraction in terms of a sum of fractions is called the method of partial fractions, and it comes in quite handy in a lot of contexts. So now we're going to use our partial fraction expansion and say that integrating the LHS now actually involves the integration of two things, each of which is a much simpler looking object than the original. And here we recall a basic result from calculus, which is that the integral of 1 over y is the log of y. Well, this is the natural log, log to the base e. If we use that to integrate these two terms, the first term looks just like that and gives you a log. The second term is marginally more complicated, but it's basically a log, and you can see how to make this work out on your own. And we get the difference of two logs here. Now, the difference of two logs is the log of, so in this case it's log of something minus the log of something else. That can be combined into the log of the first something divided by the second something else. And that's what brings us to equation 2 here. So this equation 2 is the integral of the left-hand side of the equation. We've already got the integral of the right-hand side, and the two must be equal. So we equate them and exponentiate both sides, and that gives us this expression here, which I'm going to call equation number 3. And this is pretty much what a solution ought to be. You've got the initial population size, the elapsed time, and then you've got the final population size. It's still not as nice as we would like, however. So the finale here is to do some algebra on equation 3 and rewrite it in this form, equation 4. And that is indeed the solution to the logistic equation. You can see that on the right hand side you've got elapsed time, initial population size, and the constants k and r, and nothing else. These give us the value of population size on the left at any time t. It's important that we check a few basic things about this, and these I've got down here as exercises. The first is, when t equal to 0, you ought to find that n at t equal to 0 is n0 based on our expression, and that indeed is true. The second thing is, what happens as t increases? But if you look back at our solution, you can see that as t increases, the exponential is going to get large, and it's going to get large in the denominator, which means this term in the denominator, this one involving the exponential, is going to become much larger than the other term, and so eventually n of t is going to approach the value capital K. And that's nice. I mean, this tells us that the logistic equation, you start from any population value, population size will change, and eventually it'll reach K. The last bit here, part C, is to convince yourself, using the solution, that this limiting behavior is true whether you start at a population size above carrying capacity or below carrying capacity, K. The other two problems here are just algebra to make you verify that the steps that we've outlined in these notes are in fact algebraically correct. So this is the way in which we get the solution to the logistic, and that's what we're going to use in future modules.